Hi guys, today I want to show you an example problem for dynamics that looks scary, but I promise it's actually not once you break it down. Let's get started. So we have two 10-kilogram boxes that are connected by a massless string that passes over a massless frictionless pulley. The boxes remain at rest. Okay, so at rest, that means that our acceleration is 0, right? With one hanging vertically and the other one on the inclined plane, which is at 60 degrees. The coefficient of kinetic friction is going to be 0.15. The coefficient of static friction is going to be 0.3. But giving us both, we need to know which one to use. You may use G as 10, sine 60 as 0.87, and cosine as 60 as 0.5. First step is to draw on our diagram, labeling all the forces. So we're just going to make an FBD. We are on Earth, so there is force gravity. We are on a surface, so there is force normal, and it is perpendicular to our surface. There is force tension from our string, and there is also force friction because they told us there's friction. It's what's holding it in place. The next thing that we are asked is to determine the frictional force of the box on the plane. I know that frictional force is equal to mu times force normal. Okay, and what we're looking for is force friction static, which we know is actually could be bigger than this value, right? But this is our minimum value it has to be in order for it to stay put. Okay, we already know what mu is, and since it's static, we're going to use the 0.3, but we don't know force normal, so we have to figure out what that is. To figure that out, we're going to do a sum of the forces equation, and we're going to do it in the y direction, because if I tilt my axis, and I say this is the x direction and this is the y direction, then that force normal falls directly on that delta, or in that y direction. So let's do sum of the forces in the y direction. I have force normal pointing up, and I also have force of gravity pointing down, but not all of gravity, just a component of gravity. So here's gravity, and here is our axis. This angle right here is 60 degrees. So the only component that I care about for the y direction is actually going to be this component here. And since that is adjacent to our angle here, this is going to be FG cosine theta. All right, so then we can say we want only that component minus FG cosine theta. We can say that this is equal to 0 because it's not moving. There is no acceleration, okay? All right, so I want to know what force normal is. So let's get it by itself. So I'm going to move FG cosine theta to the other side. I know how to calculate force gravity, and that is mg, and then cosine theta comes along with it. So if I'm looking for force normal, that's going to be 10 times 10 for gravity times cosine of theta, and cosine of 60 degrees is 0.5. So I just got to do 100 times 0.5, and I know that force normal equals 50 newtons. Okay, let's go back to our force friction problem here. Now I know what to plug in here. I just need to plug in my coefficient of friction, and we're good to go. So I know my force friction static is going to be 0.3 times 50 newtons, which we calculated above. So 50 times 0.3, that's going to be 15 newtons. Ta-da! It's not that bad. You could totally do this. Last one, what is the tension T on the string? Let's analyze the problem carefully before we start diving down a rabbit hole of calculations. The tension here is equal to the tension here. So if I draw an FBD of this second hanging mass, I have FG pulling it down and FT pulling it up. It is static. It is not moving. That means that these forces are balanced, which means that the force of tension must equal the weight of that second mass. So we can plug in. It's going to be mg, m2g, because it's our second mass, which means that it's going to be 10 times 10 kilograms times 10 meters per second squared. Force tension equals 100 newtons. The problem looked complicated. It was totally doable. Okay? Hope this was helpful.